Well, I want to thank the organizers for inviting me. This is quite a delight. I love NIPS. And I'd like to tell you about some of the work I've been doing in the last couple of years, me and colleagues, about how to power the next 100 years of human civilization. So let me start by telling you the world I'd like to live in. I'd like to live in a world where everyone on Earth can use as much energy as I do as a US resident. And why do I want that? Well, because it's relatively evident that a high level of energy use is a necessary condition for a high standard of living, and I'd love to have everyone on the planet to have a high standard of living. Now, is this an unreasonable goal? Is this something that would never happen? Well, let's look at the historical graph of how much power is consumed by all of humankind. Here it is. It's over the last 50 years. The y-axis is in a log scale, and it's in units of terawatts or trillions of watts. And if you look at this, it's a log linear scale, and so it's a rough line, and power consumption has been increasing by about 2.2% per year. If you extrapolate that for the next 100 years, you'll see right now we're using about 18 terawatts of power. And by 2100, if we keep going at this rate, we'll use about 113 terawatts of power, which in fact is very close to the US power rate for 11.2 billion people, which are the expected population in 2100. So my goal that I'd like to reach, it would just be an extrapolation of past energy growth. Now, it's very easy to have a graph with 18 terawatts and 113 terawatts, but you really have to viscerally understand how much energy that is. It's a tremendous amount of energy. Here's a picture of Mount St. Helens up near where I live in Seattle. It erupted in 1980 and spread ash and mud flows every which way, and so it released a lot of energy. Human civilization right now uses one Mount St. Helens amount of energy every 93 minutes. That's all of us collectively. And by 2100, that's going to speed up to one Mount St. Helens every 15 minutes. So, this is a very, very challenging problem, how to deliver this much energy to the people on the planet. Now, of course, power is a flow rate. It's an instantaneous rate. So energy is the integral of the power. So how much power do we need? Well, we're going to need something about a yottajoule. I don't know if you know about yotta. It's beyond exa and zeta. We're going to need about 0.2 yottajoules, or 0.2 times 10 to the 24th joules over the next 100 years. That's a lot of energy. A yottajoule is a lot of joules. 0.2 yottajoules is enough energy to boil off the Great Lakes 3.4 times over. And in fact, according to my calculations, 0.2 yottajoules is about 5 times the amount of energy consumed by humans since the beginning of civilization. So we're going to need a lot of energy in the next 100 years. Where's this going to come from? Well, one natural question to ask is, we have a lot of energy technologies on the planet today. Will they be able to cover this 0.2 yottajoules? Can we use fossil fuels? They're pretty abundant. Can we do that? Or if we don't want to use fossil fuels, how about low-carbon technologies or zero-carbon technologies? Will those be able to generate 0.2 yottajoules? Well, let's consider these in turn. So the unfortunate thing about fossil fuels is they don't scale. It's not that they're not abundant. They're extremely abundant. For example, humankind extracts 1 cubic mile of oil out of the ground every year. But unfortunately, when you burn fossil fuels, you generate carbon dioxide and you place it into the atmosphere. And the best climate models that we have say that there's a severely limited amount of carbon dioxide that we can put into the atmosphere without warming things up. So here's a chart or a table of how much fossil fuel energy we can use after today and the corresponding rise in global mean temperature over 1850. And there's general consensus. There's the Paris Treaty that we want to keep the global mean temperature no higher than 2 Celsius above 1850, which is at the end of the Little Ice Age. And that unfortunately means we can only supply 8% of the next 100 years' consumption with fossil fuels. That's it. Then we run out of budget. And even if you decide to be even more dangerous and go to 3 Celsius, it doesn't actually make that much of a difference. We have to use some zero-carbon solution. Okay, what about zero-carbon technologies? There's a number of them that exist. Solar power is getting increasingly common. People extract a lot of power from wind. There's other technologies you may not have heard of. There's a series of advanced fission technologies in the lower left graph. That's an example of something called a molten salt reactor. Or you can take electric plants that generate that use fuel that are fossil fuels, and then just capture the carbon. You can scrub the carbon out of their flues, just like the carbon dioxide out of their flues, just like you scrub sulfur dioxide or nitrogen oxides. So, will any of these be able to cover 0.2 yotta-joules? So here's the thing. All those technologies I mentioned, all those zero carbon sources, they all generate electricity, not fuel. And it turns out electricity generation is limited by its economics. So let me give you a brief tutorial about how the economics of electricity works. A very brief tutorial. It's a very deep subject, but just enough to sort of give you a sense of what the limits are of zero carbon energy. So, let's say you're your utility and you want to build an electrical plant. Your costs are going to be one of 2 styles. On the left, they're capacity costs. Those are costs you would incur even if you generated no electricity. You have to build your plant, and you have to incur fixed costs. You have to hire people to work at your plant, even if you generated no electricity. So the units of that kind of capacity cost are dollars per peak power, and they're linear in the peak power. So if you built a 1 gigawatt plant, it would cost about twice as much if you wanted to build a 2 gigawatt plant. Now let's say you wanted to start generating electricity. Then you start incurring output costs. So if you have to burn fuel to make electricity, that's a linear amount of fuel for your electricity. And often maintenance is proportional to the amount of electricity that you generate. So again, the units of that are dollars per unit energy out. Now I'll show you I'll re-explain this using a tool I call a power profile. So in a power profile, it shows you a time series of the output of all the plants of a certain type. Let's say this is all the natural gas plants in California that share a grid. So on the x-axis is time. Here it's just spanning a week, and the y-axis is power output. And you see these typically have diurnal cycles. They go up and down every day. Now, that green line is the capacity. You can't generate more electricity than the capacity of the plant, and the capacity cost is proportional to that, how high that green line is, or the peak. The output cost is proportional to the area, the blue, the integrated area under the curve. And so you get these 2 different costs, one that's proportional to the peak and the other one's proportional to the area. And a very useful number to think about is something called the utilization, or sometimes called the capacity factor. And that is the total energy produced, that's the area under the blue curve, divided by the maximum energy you could have possibly produced, which is essentially the area under the green line. And that utilization is how you reconcile the capacity cost and the output cost, because they have different units. So what you do is, if you take the capacity cost, you're going to amortize it over each unit of output, and so you have to divide by the utilization. And when you sum that with the output cost, you get essentially a system cost per unit energy. So the reason why I'm telling you this is I'm going to try to explain to you how electricity gets expensive and when renewable energy gets expensive. So let me tell you 2 ways that electricity can be expensive to generate. You can take the same electrical plant here, let's say you have one plant that operates at 60 gigawatts, and if you operate it mostly at capacity, it's inexpensive because you amortize your capital across many, many joules of output. On the right-hand side, let's say you only run your plant occasionally. In fact, there are such plants. They're called peaker plants. They only turn on when you have a peak in your demand. Then each joule of electricity is much more expensive because you're amortizing the cost of your capital across many fewer joules. other way of making electricity more expensive is to waste the output of your plant. So let's do this in the context of solar power, which is something called a variable power source. In a variable source, you don't get to choose when to turn your energy on and off. So, for example, you don't get solar power at night. Sorry. So let's consider solar power. On the left, there's a new curve, which is the red curve, which is the demand that is imposed by people. So people are consuming power. And again, in the middle of the day, they consume more, and in the middle of the night, they consume less. In this case, the utility can choose to have the capacity of their solar farms be about the same as the daily demand. And that's good, and you have inexpensive solar generation because all of those solar joules are being used. The trouble is, there's a gap between the solar generation and the demand, so you have to fill that in with something else, like fossil fuel. So that's not so good. So you might want to decrease the amount of carbon in your grid by increasing the amount of solar. So what you do on the right is you would triple the capacity of the solar, and that's great for cloudy days like here at hour 60. You've tripled the number of output joules. But on the sunny days, you actually haven't tripled the number of output joules. You've just wasted it. This is called curtailment. And this is a way of actually making solar power more expensive if you force it to be on when the joules aren't needed. So it turns out I've given you analysis. I've shown you a couple of graphs where the utilization of the electricity was done in isolation, but that's not right. Really, utilization is a system property. You have to estimate it for the entire grid. You have to estimate it for all technologies together, not just one technology in isolation. So here's an example. You have a green source. Let's say it's renewables. It's some sort of variable source. And you have a blue source, which is called dispatchable. You get to turn it on and off as you wish. And that might be natural gas, electricity, or hydropower. So the lesson here is as you increase the amount of variable generation, you get lower utilization, and therefore you increase the cost of your electricity. So here's two examples. On the left, the variable source in green is low, and so the peak required for the blue energy is the height of that yellow arrow, and the utilization of the blue energy is quite high. You can see that the blue energy is mostly on. Now, if you want to increase the amount of variable generation you have, for example, to decrease the carbon, you end up not decreasing the capacity of blue very much at all, but you end up decreasing its utilization. So essentially, by changing the amount of green energy you have, you're actually affecting the economics of the blue energy. That's why you have to take an end-to-end view when you analyze the cost of electricity. So you can do that. There's been a number of papers in the field of modeling end-to-end system costs. We have a paper too. The way those kind of end-to-end models work is you can model a grid for every hour of a year. And that is just a big linear program. It's not surprising it's a linear program because all of these costs are linear in these quantities like the peak or the sum. And an extra thing we added in our paper was a what if. What if you wanted renewable energy to be 60% or 80%? Well, you can add a cutting plane algorithm to force the system to find the minimum cost given that you need 80% renewable, say. So you can see our paper, look for the keyword DOSCO. Or if you're curious, we have a live tool on GitHub called Energy Strategies that you can play with if you want to try different what-ifs, try different policies or costs. So I welcome you to try that out and learn more. So let me tell you about one result we've got from running this model. So first I have to tell you the assumptions from the model. So these are plausible assumptions from of what the future might be like. Solar power is decreasing in capital costs, so let's assume that it's going to be about 60% of today's cost. The cost of storing electricity in giant batteries of some sort is going way down. So let's assume it's going to go down by a factor of 3. We'll also assume that natural gas is pretty inexpensive. In the United States, it's one of the cheapest natural gas on the planet. So let's assume it's going to go up a little bit, 20%. And then we're also going to model having high voltage power lines that will ship renewable energy across the country from places with a lot of wind to a little bit of wind. And then we're going to ask the model to compute what the marginal system cost for renewables in California, but when you force them to have a fixed fraction and you can import renewable energy in from other regions. So here's the bottom line. The x-axis is the fraction of renewables. That's you enforce it in some way via some policy. And the y-axis is that system cost, remember the sum between the capacity and the output costs. So there's a few lines here to take note of. The solid black line is the cost of electricity from a new natural gas plant. That's the cheapest plant. It's about 4 cents a kilowatt hour. And and that 4 cents counts paying off the capital cost and also paying for the fuel. If you already have a paid off natural gas plant, then the price drops to about 2 cents. So you don't have to amortize the capital cost. The blue and green lines reflect the marginal cost for adding the next kilowatt hour of renewables at that fraction. Blue is without storage and green is with storage. And you can see up to about 40%, renewables actually beat new natural gas for electricity. That's great. In fact, we're seeing that people are preferentially building renewable power plants because renewables aren't very common. But as you start to approach 100% renewables, the cost explodes. And that's because of those two effects that I told you about, that they cause the other dispatchable power to be more expensive, and you have to start curtailing, you have to start wasting renewable power. Many people hoped that storage, inexpensive storage, would solve this problem and make renewables great. And they help. They add like 5-10% to the fraction of renewables if you stay at the same cost, but they don't solve the problem. So this is a bit disappointing, but here's the bottom line. It's just repeating what I just said, that they are competitive up to about 40%, but you can't expect renewables to compete with paid-off fossil fuel. They're not below that black dash line. And there's another factor where there's something called industrial heat, where steel plants and concrete plants just burn fossil fuel just for the heat, not going through electricity. That's also about that same cost as that dashed line. And again, renewables can't displace that. So we can't rely on renewables to supply all of the 0.2 yotta-joules. So we can rely on it to supply some of it. So what are we going to do? We're going to need to change the game. We're going to need to do something kind of crazy. So let's talk about radical research into zero-carbon energy. So now we're going to have to look at less certain, more technically risky energy sources. And so we've been looking at ones that are enabled by new ideas or technologies that weren't around 20 or 30 years ago. And what we're doing is we're hoping to accelerate this radical research with all the advances we've had in computer science recently. So to put it in context, I lead a group, as Sammy mentioned, called Applied Science at Google. And that's more general than energy. What we do in applied science is we try to attack various high-impact scientific problems in biology or physics. And we work with domain experts in university and industry. We find the people who have some new idea. And then we take our expertise in large-scale computation or machine learning and go and help them on their scientific problem. So energy is one example of this. So we've been looking at energy and looking for different places to help. And we found one interesting place to help, and that's in fusion energy. So let me now tell you a little bit about how fusion energy works, and why I'm hopeful about fusion energy, and also I can get into the nitty-gritty detail of how we're using machine learning to help fusion, which might make you happy since this is a machine learning conference. Okay, so let me tell you about fusion. Fusion is why the sun shines. So that's promising. So the sun is hot enough where it's not made out of atoms, it's made out of plasma, where it's so hot that the electrons separate from the nuclei. And at the sun's core, it's very intense. It's got a temperature of about 15 million Kelvin and has a pressure of about 250 billion atmospheres. And under these conditions, the nuclei actually fuse together. They smash into each other, and they form and they resplit into different nuclei. And those output nuclei have less mass than the input nuclei. And because of Einstein's E equals mc squared, you get energy out. You get a lot of energy out. In fact, this is incredibly energy dense. So this 0.2 yotajoules we need for the next 100 years, if you're going to fuse deuterium, that only requires 100,000 metric tons of deuterium, which can be found in 6 cubic kilometers of water. That's, for 100 years, that's really very feasible. Or if this proton-boron reaction turns out to be feasible, you only require 3.3 million metric tons of boron. That sounds like a lot, but it's only 7 months of world production of boron. So this fusion has the potential of being an inexhaustible energy source. So here's the problem. No one knows how to make it work. It's been pursued for 70 years, and it's a very, very, very difficult engineering problem, right? Because creating conditions like at the center of the sun is incredibly tough. Here's a picture I found from 1951 of some physicists making a ring of plasma, and on the right-hand side you can see it starts to get kinks, because plasma likes to go unstable. It's very difficult to make a stable shape of plasma. Another problem that happens with plasma is you get heat loss. Remember, we're trying to make these objects that have tens of millions of degrees temperature, and it's very easy for the heat to just leak away and the system to cool off. So despite literally decades of research, no one has ever gotten more energy out of a plasma than if used to maintain a plasma condition. Now, there are many approaches to fusion. We're working on one of them, but just to review them briefly, there's sort of tokamaks. These have to do with like the shape of the plasma. That's the common one that's used, for example, in the European ITER project. Other people are thinking about inertial confinement, where they actually take a little pellet of deuterium and shoot laser beams at it and compress it until you get to fusion conditions. On the lower left, there's a set of plasmas called compact toroids. I'll talk about that more in a minute. And interestingly, I don't know if you've heard of this, there's something called the Farnsworth fusor. It was actually invented in the 60s by the same person who invented the television set. And you can actually do fusion on your desktop, but you are forever doomed to never get more energy out than you get in. So, what are we doing? Well, we're not fusion experts, so we've teamed up with a company that are a bunch of fusion experts. The company is called TAE. And they've been around for almost 20 years, and they have specialized in this specific plasma architecture called an FRC, a field reverse configuration. And they've been doing progressively larger, higher energy experiments into the FRC. There's a diagram of one of their machines on the right. And so we're working with them to help apply computer science to see if we can accelerate their progress. Here's a picture of their latest apparatus from end on. It's actually quite a long apparatus. It's more than 20 meters long. This is the end. The apparatus is named Norman because it's named after Norman Rostocker, who is a plasma physicist and one of the co-founders of TAE. So why did we choose TAE? Well, they have two really nice properties. One is they have, speaking as a statistician or a machine learning person, they can do rapid experimentation. In the last 20 years, they've built 5 machines, and they've accumulated 70,000 experiments. They can actually do an experiment about once every 10 minutes. And in fact, on that Norman machine I showed you, they've done about 3,000 experiments since July. So it's a nice way to gather a lot of data and do a lot of exploration. The other reason why we like working with TAE is the data they've gathered so far suggests a good scaling law. So let me tell you what I mean by a scaling law. I'll describe it, but in summary, it's how difficult is it to get energy out of fusion? You can actually write down very simple formulas that try to predict that. So let's get into that. It's always nice to be in a field where you have a metric, and there's a metric for fusion success, and it's called Q. It's very simple. It's the ratio of the energy out that you get from fusion divided by the energy in, the energy required to maintain those plasma conditions. And everyone is chasing after something called break-even, or scientific break-even, and that's when Q is greater than 1. That will be quite an accomplishment. The highest Q so far was done by the jet tokamak. Very briefly, it attained Q equals 0.67 back in 1997. Now, remember, way back at the beginning of the talk, we want to compete versus fossil fuels. So it's not enough to just get one extra joule of energy out after spending $1 billion. So you really need to get a lot of energy out. You have to get Q of 5 or even higher. Because the higher the Q is, essentially for the same capital cost, you get more watts, or reciprocally, you have less capital cost per watt. So remember, the capacity cost goes down. And that means the system cost goes down, which means maybe we can compete with fossil fuels. So the hope is that this FRC will give you very high Q. Now, what's the criterion for Q equals 1? It turns out that the plasma physicists worked this out back in the 50s and the 60s. There's another criterion called the triple product, which is predicting when fusion can predict net energy. And that is a product of the density of the plasma, which is the number of nuclei per unit volume, times the temperature of the nuclei, times something called the confinement time. The confinement time is in units of time. It's the amount of energy that's in the plasma divided by how quickly you lose your heat. And depending on what your fuel cycle you have, there's some constant you have to be bigger than. And so if the product of those three numbers is bigger than some constant, you should be able to get Q equals 1. So now this is where the scaling all comes in, because these three numbers aren't independent. In fact, it's not surprising that because tau is a heat loss and T is a temperature, they're related. So you need to have plasma that's both stable enough, in other words, it has to be long enough, and it has to be hot enough, and then you can actually get a net energy out. And it turns out there's two different kinds of scaling laws. If the world is friendly to you, you get the green scaling law, where they're positively correlated. Where as you make the temperature, as you make the plasma hotter, you make it more stable. Otherwise, if you're in an unpleasant world, as you have to trade off temperature and heat loss. So since you're trying to make the product of both of those be high, that's kind of unpleasant. As you make your plasma hotter, you lose on time, or vice versa. So this is a very unpleasant place to be in. Preliminary data from TAE shows that this FRC plasma has this surprising scaling law where the confinement time actually goes up quadratically with the electron temperature. That is counterintuitive. It says that the higher your temperature is, the lower the heat loss rate. And it's a strange property of your plasma. It's sort of like saying that you have a bathtub, and the more water you put into the bathtub, the less water comes out the drain. But it's a property of the specific architecture of the FRC. If you go back and look at the same scaling law for tokamaks, you're back into whack-a-mole. In other words, you have to trade off temperature and confinement, which is, again, a really tough problem. This is why tokamak engineering is not at all easy. So we're collaborating with TE, and we have two main goals. The first goal is we're helping them with computer science to try to verify that scaling law. Remember, they've only verified it up to about 1 million Kelvin. We really need to verify it up to tens of millions of Kelvin, so about 1 to 2 kiloelectron volts. And then once we verify that scaling law, we really want to estimate that Q for the commercial reactor. In other words, we're trying to estimate, is this actually going to be able to displace fossil fuels or not? So that's the collaboration, and that's a little tutorial about fusion. Now you may be wondering, well, how can machine learning help? Well, there's two different projects we're working with TAE. One is essentially optimization, but it's really about exploration. And the other one is about inference. So let me go through both of those projects. So the first project is a little bit like hyperparameter tuning, but not. Here's a picture of the Norman apparatus. It has thousands of parameters, and they're not well characterized, because the way Norman works is you first inject gas at the two ends, and then you ionize the gas to make a plasma, and then you you accelerate the two plasmas from both ends, and so you have to choose how quickly those accelerate. So there's a bunch of magnets that are accelerating the plasma. And once the two plasmas collide, you have to maintain that plasma in the center with a choice of magnetic fields and electric fields. And on top of that, you're shooting that plasma with neutral beams, so neutral beams of hydrogen, and you have to set the parameters of those neutral beams. So I mentioned it was like hyperparameter tuning, but it really isn't. And I think actually what I'm about to describe is actually more general than fusion. I keep running into this. You don't really have a known space. It's not like you have a nice box that you can draw samples from. The physicists say, let's start here where the green star is. And you just don't know. You know that you know certain things because they built the machine. So there are certain parameter settings you just don't want to use. You don't want to overload the power supplies of the capacitors. So don't go there. Don't go past where the red hyperplane is. But there are other settings that you can set the machine to be that actually hurt the machine. So you have this beautiful machine, and you run an experiment, and a bright flash goes off. I've seen this. And then the physicists look very worried, and they run out and they examine the machine, and they might have to spend hours or days or, in very worst case, weeks repairing the damage you just did by doing a bad experiment. So we want to be very careful about setting parameters that we don't want to break their machine. So really, this is not an optimization problem. This is an exploration problem. We're trying to figure out what's the shape of the polytope that is sort of safe to do experimentation. And it's not completely hopeless because it's as you get close to the edge that you can tell the physicists in the room get nervous. So they will tell you when you're getting close to the edge. They just don't quite know where the edge is. So in fact, we came up with something called the optometrist algorithm, which is essentially Markov chain Monte Carlo, but with human preference on the inputs. And let me give you a little animation of how it works. So you start someplace, and then you add a bit of noise with some parameter setting. So you set all the parameters. You add a little bit of noise, and the physicist said, that was great, never do that again. So you walk back and you do another perturbation, and that's better. It's more interesting. And there might be an objective metric, or there might be just subjectively the physicists like that more. So you perturb that again. Oh, that's not as interesting. You go back and that's even better. So what you're doing is you're sort of climbing a hill of human preferences with the physicists in the loop in the control room deciding on how to set the parameters. And this seems to find both interesting regimes that were unexpected and avoids unsafe areas. So in fact, we did this on the previous machine to Norman, and we found this unexpected rising temperature regime that the TAE physicists didn't expect at all. They didn't expect their ion temperatures to actually grow to be 1 kiloelectron-volt. And they were actually very happy because that gave them confidence in actually building Norman, which is now built. So we published that. That's the first machine learning project. The second one has to do with inference. And it turns out that when you're trying to do this experimental plasma physics, you spend a lot of time debugging your plasma. Here's an image of your FRC plasma, and ideally it's perfectly stable in the center. But sometimes things go wrong. The plasma tilts or wobbles around, or there's some pathway that lets the plasma cool off, or it might bounce and touch the walls. And the physicists want to know, why did that happen? Well, it turns out they're not just doing things totally blind. There's many sensors, or what they call diagnostics, available. You can measure the magnetic fields. It's impossible, by the way, to touch the plasma because it's millions of degrees Kelvin, but you can do all these indirect measurements. You can actually use high-speed video cameras, which have very wide field of view, but they're very narrow spectral band, or there's these things called bolometers, which can look at a very small field of view, but integrate across all of the spectrum. There's even a property called Thomson scattering. You can shoot a laser beam into the plasma and estimate its electron temperature along one line. So these are very sparse, informative, but very sparse, both in time and space, sensors. And so, of course, we decided to do a Bayesian inversion, where we're trying to infer the hidden state of the plasma, which consists of where it is, what's its shape, what's its temperature, and what density does it have, again, going back to that triple product. And the way this works, it's what you might expect from a Bayesian setup. We have a 3D probabilistic model of plasma, or 2.5D if we're trying to make it be faster. And we have a generative model based on the physics of the sensors. We have a generative model of the sensor data. We compare what the generative model is predicting to the actual sensor data, and we use that as a feedback loop to update the probabilistic model. But of course, that's sparse data. We're not doing maximum likelihood estimation. So we use a prior over the plasma state that involves physics knowledge. So, for example, we enforce smoothness along magnetic flux lines. And the way that works is we do a relatively large-scale stochastic variational inference. So we assume a functional form over the posterior. So you may be familiar with this from variational inference. We maximize the elbow, the lower bound of the evidence, and we use stochastic gradient descent. And the nice thing we use is TensorFlow. TensorFlow is a nice way to parallelize gradient descent. So we map this Bayesian inference to 10 GPUs and essentially do variational inference. And the automatic differentiation part of TensorFlow is very handy because we have to take derivatives through this physics code. The nice thing about Bayesian inference is you can get error bars, which is helpful to tell the physicist like whether you actually know what's going on in the plasma, or if you're just puzzled, or if the algorithm itself is puzzled. But with variational inference, it doesn't give you good error bars, so we calibrate it using simulated plasma. The nice thing is we can get a solution in less than 5 minutes, so we're actually keeping up with the pace of experiments that TAE is running. Here are just some preliminary results. Given 2 cameras and all the magnetic sensors, we can reconstruct the emissivity, in 3D, how much the plasma is glowing and what the magnetic field is inside the chamber. And this is ongoing work. We're going to place this plasma debugger live inside of their experimental loop. So looking forward to this collaboration, next year I called the Year of Science, because going back to the scaling law, we're going to try to do everything we can to maximize that electron temperature, and we're going to try to verify the scaling laws up to high temperature where we're getting close to actual fusion temperatures. And the outcome will be a precise estimate of Q at commercial scale. Then after that, TAE will build yet another machine that will, if all goes well, will actually demonstrate break-even fusion, so that's exciting. And that engineering will also help us get more precise costs about how much fusion power will be. So I worked on this project some. It was really fun. Are there other projects like this? Well, it's tricky, right? You want to work on a problem that has a lot of real-world impact. You don't want to just solve 0.001% of the climate problem. So you want to find a problem that can somehow displace or negate, say, 10% of the fossil fuel usage. But we're also machine learning and computation and statistics people, so we want problems that have a large number of experiments. It turns out it's kind of hard to find projects in this intersection, but when you find them, they're really interesting. So I guess in conclusion, just go back. We're going to have to figure out how to get 0.2 yotajoules of zero carbon energy somehow. There may be many possible pathways. One that we've identified is fusion energy, and we have combined fusion energy with machine learning, and hopefully we'll have a large impact in the world. We're not done yet, but we have hope. And the question I want to leave to the audience is where else can ML help? There might be other pathways to get to the 0.2 yotajoules. So that's my talk.
Thanks, John, for this great talk, and a bit scary as well. We have plenty of time for questions, so there are mics in all the aisles. Please come to the mic and ask all the questions you would like to.
Hi. Couple questions. First, just you talked about fusion. What about fission? Oh, you can't hear me? Yeah. But actually, I have another question I'm a little bit more interested in. This is just a basic question about the mechanics of fusion. So, as the fusion is taking place, the original molecules, or would it be molecules that you had are being replaced by these other molecules, right? That's how the energy is produced. So do you need to like add more of the original mixture of molecules?
That's right. There's something in fusion. The question was, do you have to sort of keep feeding fuel in? Well, it's slow because it's so high energy density, but it does accumulate something called ash. That's what they call it. I mean, it's like a wood fire, except it's fusion. And so you do have to occasionally restart the reactor and have more. I mean, it depends on the fuel, right? Deuterium tritium is complicated. I can tell you offline, but you do have to. It's not a perpetual motion machine. You do have to keep feeding fuel in. And you asked about fission, or?
Yeah, just do you think that has a role to play as well? Just because you didn't mention it at all in the original talk that I know.
Oh yeah, sorry. I had a limited amount of time. I can go on for this for hours. Advanced fission. The future cost of advanced fission is very uncertain. The most optimistic estimates say that it could displace, similar to renewables, new plants, but not old plants. So part of the reason why I didn't bring it up is I've been scratching my head. There doesn't seem to be a very good large experiment thing to try there. So it just wasn't, there just wasn't anything I could try. But it does have a future as part of that 0.2 yotta-joules, if it becomes cheap enough.
Hi, thanks so much for a great talk. I was wondering about the renewable energy, the graph where you show that the cost of increasing renewables actually increases the cost of per unit of energy produced, mainly because of the variability of renewable energy. And so I was wondering if you think it's realistic to target the variability of renewable energy, and if that would give like similar gains to any other proposed solution.
Yes, you exactly identified the problem. It's the variability. If you could figure out how to get renewable energy that was what they call base load, which is 24/7, that would solve the problem. In fact, that model, that's part of the reason why I mentioned the high voltage DC lines across, because if you import wind energy from the Midwest to California, it actually balances. It's sort of the noise balances out and the variance reduces. So that actually does help, and you definitely need to do cross-continental wind importation above about 50% wind. But it's just hard to get it to be a perfect flat. But if you could somehow come up with renewables that was baseload, problem solved.
What about geothermal?
Oh, geothermal? Okay. So the question was, what about geothermal? So, geothermal's great, but it's only cost effective in what they call hydrothermal areas. So in other words, areas which are that already have a lot of water passing through them. There's something called dry rock geothermal, where you actually inject water down, and there's been some work on it. But the trouble is the economics just don't work out. It'll be roughly as expensive as today's nuclear power, which is very uncompetitive. Because you're right, I mean, there could be a vast amount of geothermal if you can. The trouble, it all boils down to 5-kilometer wells, which get you down to 300 Celsius, cost a lot of money, and it just doesn't compete economically. It's just a shame. So you're limited to the amount of geothermal you get out of hydrothermal.
Hi, I'm a data scientist with Shell, and my question is, what are your thoughts on distributed energy generation and distributed grids? And a lot of people see it as a big potential opportunity for machine learning and deep learning to optimize grids.
The question was about distributed energy. I had to cut that from my talk for time. That might raise, there's good and bad things. That might raise the amount of renewables, because the cost point is not the cost of the natural gas, it's the cost that you pay to the utility, which residentially might be 11 cents a kilowatt hour, or if you're industrial at 7 cents. The downside is that you can't average. If you're just hoarding the electricity by yourself, if you're not part of a grid, you have to make your own capacity that covers your own peaks. Now, there have been proposals. In fact, back in 2014, there was an invited talk by Arun Majumdar about bottom-up grid, where he was talking about that. but what it does, it might be able to increase the renewables above 40%, but then you actually have this thing called, it's like adverse selection, where as more and more people detach from the grid becomes more and more expensive, and that means more people will detach from the grid. So I don't know how it's going to end up, but it is possible it might go above 40% if distributed things like distributed PV become common.
Just a quick follow-up question. Do you see there's an opportunity for machine learning to optimize peak loads for distributed grids?
The question is there machine learning? Maybe there might be if you're trying to predict, for distributed, you might be trying to predict how to charge and discharge your own battery, maybe. I don't know.
Thank you.
Mm-hmm.
Okay. So we have to go on to the next event, and let's thank John once again. If you have additional questions, come up now. Now, I'd like to invite everybody to the Pacific Ballroom.